Okay, so now let's go, and our CFL is, let's go back up to CFL of 2, and let's actually build in Leapfrog. Now, Leapfrog is slightly different. Leapfrog says, I need now, instead of one initial condition, I really need 2 initial conditions. Now, I'm going to cheat a little bit here, because to get 2 initial conditions, often what people do is what's called bootstrapping. So this thing isn't going to blow up on you in one step. So you can often use just Euler to get from 0 to delta t, and then those are your 2 time slices, 0 and delta t, and then you move forward into the future from those. But here, since I kind of know what the solution looks like, what I'm going to do is just come here and say, okay, I also need u0, and I also need, let's call it u1. u1 is equal to, and it turns out it's not so hard to fix up. What this thing does is moves over delta t because the speed is 1. I'm just going to use the exact solution. And I have a u0 and a u1. And these are my first 2 columns of the solution vector. Okay? So I have, so u0 is my slice in the past. u1 is my current slice in a way. And I'm trying to get my solution now to delta t into the future from this. So I write them out. Now I come down to here. Here's my little routine. And let's go ahead and just copy and paste for a minute, because we're going to come back and have to use this. What I'm going to do is do this. Now, my solution, let's call it u2, is equal to what it was. So u1 is my current time. u2 is my future. u0 is my past. And now, in this case here, you're going to have CFL A times u1. Let's just double check that. Yeah. That's it. But now, what do you got to do with this? This isn't what you want anymore. So let's think about what we got to do. Now we're going to so my current point, my current future, my current time becomes my past. That's u1. And my future point becomes my current. Now, the order you do this in is very important, right? So the first thing you want to do is say, well, my past is now my current, and then my current is now my future. Don't do it in a different way. In other words, if you said this one first, you'd say, my current, right, my future is now my current, and then my current is now my past. It means you wrote everything as u2. So just make sure you do it in the right order, okay? And then after you're done, you just write out what your current is. And now this is j plus 2. And now that's how you're going to step forward. T minus 2, I believe. There you go. That's it. Leapfrog. 2, 2. Not that big. Not that much of a difference. Run it. Here is the result. So, same kind of stuff. This wants to blow up a lot faster, however. Again, all numerical garbage, all things that are just generated by an iteration scheme itself. That's it. So the iteration scheme itself, in some sense, you can think of, has its own, for lack of a better word, physics to it, right? The engineering, you can't just discretize anything and say, well, under discrete, anything will work. No. What's clearly demonstrated here is the iteration scheme itself has some phenomena associated with it. Discrete dynamics are quite rich and complex. And if you don't keep your CFL in check, this is what happens to you. This thing will blow up. Okay? So there you go. That's badness. I like to think of it as badness. And now, remember the CFL here was 2. This thing should, in theory, work if it was 1. So all I'm going to do is just cut my dt in half. Oh, look at that. This I know is correct because, in fact, it's the exact solution. There you go. Wave traveling to the left. One-way wave equation. Okay? Okay? So the solution to this thing exactly, you can write it down, is just whatever the initial condition is, and it just slides over with a group velocity. It never changes its shape. So this is your Gaussian that you started with. It just moves to the left. That is the correct solution. Okay? So there you go. You just see, just by changing step sizes, changing schemes a little bit, that's correct. The other stuff's completely wrong. Like I said, if you let that other stuff run for a while, you'll just see that it blows up. Okay? Everybody good with that? That's how you program these schemes up. And like if you do FTDT calculations, which are finite difference time domain in electromagnetic field theory, that's one of the most standard ways to do compute electromagnetic fields is through basically using a leapfrog scheme similar to this here.
So if you're not, like you don't intuitively know what a legitimate answer is, and you're using these methods, what are the techniques to check whether you're looking at garbage or amazing insights into reality?
Yes. We all hope for amazing insights into reality. And so we always hope that it's not just garbage. So how do you know? Well, here's how you know, kind of. And we have already done it, actually. I'm not going to say I already answered it for you, but in a way I sort of did. So let's do the following. Let's violate CFL. Now, the standard thing you want to do is what's called a convergence analysis. You say, I took a DT, and what I got was this. And then I ask the following question. If this really is the solution, as I crank down my delta t and my delta x, everything should converge, right? If, in theory, delta t and delta x, as they get smaller and smaller and smaller, you should be getting more and more and more accurate. Everything should be converging onto the solution. What you see here is this, and you go, hey, is that super awesome new physics or not? One thing you could do is just cut your delta t in half. Right? Because if you keep cutting delta t in half, it should be converging. So for instance, let's not quite it. Okay, time out. Okay, let's not quite cut it in half. Let's just go to 0.15. Here's my result. Ooh, it's changed. In fact, it even looks stable. And you can say, oh, is that really true? Well, let's run this out a little bit longer. Ooh! Did I say it was going to blow up? I think I did, didn't I? Do you see this up here? Do you see that 10 to the 11? Okay. So it looked really harmless, didn't it? And I say, whoa. Okay, so now, again, I just brought it down a little bit. So you kind of say, look, if I change my delta t, it had a huge impact, right? I went from 0.2 to 0.15. This was normally the clue that something's not right. It has not converged to the solution. Whereas, once we drop it below the CFL condition, you say, okay, well, let's try to see if I can get this right. Let's go to 0.1. Here's the solution. By the way, that's just periodic boundary condition effects, right? Because it went through one side of the boundary, came out, starting to come out the other side. Okay? But just in case that freaks you out, and we're going to take more steps, let's just go back to the 4. And I say, okay, that was the wave traveling to the left, and I can keep cutting this in half. Now let's do 0.05. Same thing. So in other words, as I keep cutting delta t down, this won't change anymore. That's the idea behind a convergence study. So whenever you see something, and you're kind of like, is that really true? Cut your delta t down. One easy way to do it with OD45 is just to go in, and you've already done this, right? You play around with your tolerance settings. Your generic tolerance settings are 10 to the minus 6 accurate. Put it down at 10 to the minus 7. If your solution changes, you know you don't have a convergent scheme. Okay? This is how you check these things. You take delta t small enough, this thing should not change below some value. You should always get the same dynamics out of the system. Yeah?
How important was the U1 that you guessed?
How important is the U1? In this case, it turns out I'm guessing the exact solution. If you don't do that, it gives you a little bit of a problem. But that's fine. If you do forward Euler to get it, you'll be fine. So if you use forward Euler to get one delta t into the future, I'm just too lazy to write that. But, so yeah. You don't want to typically guess your U1 if you don't have to. Okay, So let's. So there you go. This is a one-way wave equation.